So this lesson is about the law of conservation of momentum, which is a really powerful tool that we're adding to our momentum toolbox. And one thing that's unique about this compared to the other topics in momentum we've discovered so far is this is a tool or a law that can be applied to a collection of objects. So we're no longer just looking at one object at a time and saying, what's its momentum? How's its momentum changing? What impulse is it feeling? We're looking at multiple objects that are interacting with each other. And we're saying not just what's the momentum of this one particular object, but what's the momentum of the whole collection. Now, one thing about the law of conservation of momentum is you'll find there are situations where it's very useful and very applicable. Some collections or some systems lend themselves really well to using this tool. Others not so much. So if we want to identify which systems benefit from the use of conservation of momentum, we're going to look first at some forces. And we have to classify some different types of forces that might exist on a system. So one thing we need to know about is something called an external force. External force is a force that comes from outside the system. And I like to give an example of a couple of skateboarders who are skating towards each other and they crash. They get in a head-on collision. I'm going to draw that out quickly, and then we'll look at the forces that exist on all of the objects in that collection or in that system. So here's two skateboarders. They've been skating towards each other and the tips of their boards have just touched. So they've only just collided. And at the instant of this collision, there's going to be a few forces acting on them. So as you're probably pretty used to by now, both of these skateboarders will have the force of gravity acting on them. And because they're being supported by the ground, both of them will have a normal force pushing up on them. Now, the other force they're experiencing is from each other. The left skateboarder is going to be pushing on the right skateboarder, and the right skateboarder is pushing on the left skateboarder as a result of this collision. I don't particularly care what we call that force, but we're going to use a different color for it. And I'll just call it the force from the crash or the force from the collision for now. Okay, so let's look at the colors I've used here. I very intentionally used two different colors for these forces. Fn and Fg were all in red, and the force that each skateboarder exerts on each other is in green. So what I've been trying to do here is I've been using red for external forces and green for internal forces. So if we consider our system to be the two skateboarders, that's our collection of objects, then this crash force is coming from inside the system. It's coming from one of those two objects. Whereas the gravitational force, well, that's coming from the Earth, which is beneath them down here. That's not part of our system, so it's an external force. And the normal force is coming from the pavement here. That's not part of our system, which is just the two skateboarders. So that's coming from outside the system. That's an external force too. Now, in this situation, you guys should be able to see that force gravity and force normal for this skateboarder will cancel out. And force gravity and force normal for this skateboarder will also cancel out. So we have a situation where all of the external forces add to zero. That's an important thing to notice, and that makes this what we call an isolated system. So an isolated system is a system where all the external forces add to zero. A system where all the external forces add to zero. So why are isolated systems so special? Why do we want to know about them? It turns out that the law of conservation of momentum is particularly useful for isolated systems and not so useful for systems that aren't isolated. So let's look at these isolated systems more closely. So in an isolated system, two colliding or exploding objects will experience equal and opposite force. Remember, if we looked back at this isolated system we had here, because it's an isolated system, the red forces cancel out. So all we have left are these green forces. And because these green forces are coming from objects within the system, they'll cancel each other out. This is sort of Newton's third law at work here. If the left skateboarder pushes on the right skateboarder with this force, then the right skateboarder has to push on the left skateboarder with a force that's equal and opposite to that. So if we can just make sure that these red forces cancel out, making it an isolated system, then we know that these green forces are going to cancel out because of Newton's third law. So if these objects experience equal and opposite force, we can therefore say that they must experience equal and opposite impulse. Why can I say that? Well, remember, here's our formula for the principle of impulse and momentum. And this part here is the impulse. So impulse is the force times the time. We just said that the forces were equal and opposite. So that means as long as the two forces act for the same amount of time, the impulse will also have to be equal and opposite. Equal and opposite force, but same time, means I have to have equal and opposite impulse. And when you think about it, it makes total sense that these forces will act for the same amount of time. If we look at our skateboarders, it would be very hard to imagine a situation where the left skateboarder pushed on the right skateboarder with this force for 3 seconds, but the right skateboarder only pushed on the left skateboarder with this force for 2 seconds. Because these forces both exist because of each other, Newton's third law, they kind of have to exist at the same time. Whenever one force exists, the other force exists. And whenever the other force exists, the first one has to exist too. So basically, as long as the skateboarders are in contact, both of these forces exist. And the instant the skateboarders aren't in contact, both of these forces disappear. So that ensures that those forces will have to be there for the same amount of time. And since they're equal and opposite forces, that gives us an equal and opposite impulse. Okay, so if we have equal and opposite impulse, then this part here tells us we need to have equal and opposite change in momentum. So we can conclude that in an isolated system, two colliding or exploding objects experience an equal and opposite change in momentum. So this leads us to another conclusion, which is the law of conservation of momentum. That tells us that in an isolated system, the total momentum cannot change. Or in other words, momentum is conserved. The objects can experience change in momentum individually, but those changes will be equal and opposite. So, for example, if this guy gets a change in momentum of 12 kilogram meters per second to the right, then this guy has to get a change in momentum of 12 kilogram meters per second to the left. If I add up those changes in momentum for the whole system, I've got 12 right, 12 left, or positive 12 and negative 12, and they will cancel out. So the total momentum of the system will not change. The way we write this in formula form is that the total momentum at the beginning has to be equal to the total momentum, the sum of all the momentums for all the objects in the system at the end. Okay. Let's look at some other systems that may be isolated and where we can maybe apply this. And I'll show you sort of a problem-solving tactic. Let's look at example 1 here. So this is an example from the game of pool. We've got a 0.25 kilogram cue ball. It's traveling east at 4.5 meters per second when it collides head-on with a 0.25 kilogram 8 ball traveling west. So we've got these two balls traveling towards each other and they collide. After the collision, the cue ball is now traveling west. What's the velocity of the 8 ball? So the balls come in together like this. They presumably bounce, and this ball heads back in the direction it came from. What is this ball doing? Which direction is it going, and how fast? So first of all, let's see if this is an isolated system, because for isolated systems, we can use our new formula. So I'm going to draw this out. Here's the pool table with a couple of balls sitting on it. There's our cue ball. There's our 8 ball. And And I'll draw now the forces acting on them. So this situation is really similar to the skateboarders we looked at in our last example. Not all the systems we look at will have the exact same free body diagram, but in this case, these two more or less do. So there's my free body diagram. Again, we've got normal and gravity acting up and down on each ball. And then when they collide with each other, there's this Newton's third law pair of forces that each ball exerts on the other one that are equal and opposite. Our system is the two balls. So these two forces are coming from within the system. And these red forces, our external ones, are coming from objects that are outside of the system. In this case, they're coming from normal forces coming from the pool table and gravity forces coming from the earth. So looking at this diagram, I can say that the external forces are all balanced, right? Gravity is canceled by normal, gravity is canceled by normal. Since the external forces are balanced, I can say that this is an isolated system. Okay, and the great thing about isolated systems is in an isolated system, momentum is conserved. So that means we can now use our new tool, the law of conservation of momentum. But before I jump to the equation, I want to show you how I like to set up problems like this. There's sort of a problem-solving approach that I find really useful when we're doing conservation of momentum problems. I start by drawing a chart, a T-chart, if you will, and labeling the sides initial and final. Initial being what happens before the collision, and final being what happens afterwards. And here I'm going to draw another diagram really quickly, only here in this diagram, I'm interested in the momentum now. So rather than drawing the forces, I'm going to draw the things I need to find momentum, namely the mass and the velocity. Okay, so there's my two balls with their masses and their velocities, 4.5 meters per second east and 5 meters per second west that I got from the problem right here. That's what's happening initially, so just before the collision. Now I'm going to draw what's happening at the end, just after the collision. The balls seem to have kind of collided and separated based on what's happening in the problem. The cue ball is now traveling west, back the direction it came from at 2 meters per second. And I'm not sure what the 8 ball is doing. That's what I need to try and find out. So now it's time, I think, to get to doing some actual solving. Let's get some numbers and some equations involved here, if we can. So I'm going to write our formula from the previous page for the law of conservation of momentum. I'm kind of writing the formula straddling both sides of my t-chart to kind of show that this side is everything that's happening before the collision, right? Here's the balls before the collision. Here's the calculation of the momentum before the collision. And here's my final side, diagram for after the collision, and here's the momentums for after the collision. Now let's calculate some momentum. So momentum is mass times velocity. So I'm going to have one momentum is going to be mass of the cue ball times velocity of the cue ball. And I'm going to have the mass of the 8 ball times the velocity of the 8 ball. Those are my two initial momentums. And as the formula suggests, I'm going to sum them. I'm going to add them together. Then on the final side, I've also got both objects. And perhaps to be proper here, I should distinguish between these two velocities, or between this velocity and this velocity. These are different because this is initial, this is final. So I'm going to call this velocity of cue ball initial, and this can be velocity of cue ball final. Similarly with the 8 ball, initial and final. So let's put numbers in. Okay, one thing I want you to recognize here is that because these velocities are vectors, note I've got these vector hats above them, direction is really important. In this problem, which is a 1D problem, we're going to express direction by using positives and negatives. So I have to pay close attention when I plug in these velocity numbers to whether they're positive or negative. This 4.5 was positive because it was going east. This 5 was negative because it was going west. This 2 was negative because it was going west. And this V, I'm not sure what direction it is. I kind of have a hunch it's going to be going east, so positive, but we'll find out. We'll solve for it. Now, it's time to do a little bit of math and simplify this. So on the left side, I have negative 0.125. And on the right side, I have that will be negative 0.5 plus 0.25 V. I'm going to bring this negative 0.5 over to the other side, which should give me 0.375. I've stopped drawing this line down the middle now, because since I moved this guy over to the other side, the stuff over here is no longer just the initial stuff. And the stuff over here is no longer just the final stuff. I've started swapping numbers to the other side. So this line no longer divides initial from final. We're just kind of doing math at this point. Dividing both sides by 0.25 should give me my answer, which is positive 1.5. Or 1.5 meters per second east. So the 8-ball, after the collision, is heading east at 1.5 meters per second. Let's do one more question right now. Let's tackle this one up here. Example number 2. Here we've got a bullet striking a wooden block and embedding itself in the block. This is a bit different because here, the two things that collide, the bullet and the block of wood, actually get stuck together and travel off in the same direction together. Whereas in our original problem, the two things that collided bounced apart and headed off in different directions. So there's two sort of styles of collision problem here. One where the objects bounce apart, one where they stick together. That means things will look a little bit different when we get down to our math, but the approach is still the same. So let's set this up as with my T-chart again. And I'll do a little diagram. Okay, so I've got a bullet of mass 35 grams moving at a velocity, I don't know, headed towards a chunk of wood that's just sitting there stationary, that's 5 kilograms. After the bullet hits the wood, I have a collision. Here's what we're looking at after the collision. The bullet is now stuck in the wood, and the two objects move off together at 8.6 meters per second. And we want to know what was the original speed of the bullet. This guy right here. Now, the astute watchers out there will be looking at this situation and trying to do a bit of a force diagram like we did over here. And they might even say, wait a minute, this bullet has FG acting down on it. But because it's airborne, it has no FN acting up. So in this system of the bullet and the block, we can't say that the external forces add to 0. So we can't say it's an isolated system, so we can't use conservation of momentum. Now, theoretically, that's all true. But here's the thing. Being a good physicist or a good engineer, a lot of the time is about trying to figure out which simplifications you can make, which assumptions you can make, that even if they're wrong, they're insignificant enough that they don't really impact the result. And I'm going to try and argue here that, yes, although this is not an isolated system, it's close enough to being isolated that we should pretend it's isolated. Think of it this way. So yes, gravity is acting down on this bullet and normal is not pushing up. So gravity will have an effect on this bullet from before the collision to after the collision. But I think that the effect of gravity during that really small time period, because we're looking like just 1 instant before the collision here, like a millisecond before the collision, to like 1 millisecond after the collision. It's not a long period of time. The shortest time period you can kind of imagine. And during that time, I don't think gravity is going to deflect this bullet very much. Yeah, if we gave gravity, a couple seconds, it would pull this bullet all the way down to the ground. But in, 1 millisecond, the tiny amount of time between initial and final, before and after the collision, the effect that gravity has on this bullet is going to be small because gravity, it takes time for that effect of gravity to build up. However, the effect the bullet has on the block due to these internal forces is going to be huge. The block wasn't moving at all, and now it's moving at 8.6 meters per second. So because the effect from these external forces is really small compared to the effect from the internal forces, we're going to basically ignore the external forces, which means they effectively all add to zero, which means we can pretend it's an isolated system. This may seem a bit like cheating. It might make you uneasy, but you've probably done this a lot in the past. A great example is air resistance. In physics, we almost all the time solve problems that are happening on Earth, in Earth's atmosphere, where there is air, and therefore there is air resistance. But we so often ignore it. Not because it's not there, just because we know the effect is going to be really, really small. So we can get a very, very accurate answer by just ignoring it. Same thing here. This is not going to be truly an isolated system, but because the effects of the parts that make it not isolated are so small compared to the other effects, we can get a really, really accurate answer if we just ignore those effects and pretend it's isolated. So let's go ahead and do that. Pretending it's an isolated system, assuming it's an isolated system, neglecting the effects of the external forces, we can say that momentum is going to be conserved. So for my momentum initial, I've got the wood block, which is not moving, so it has no momentum. And I've got the bullet. Its momentum will be its mass times its velocity. I don't know the velocity, so I'll just write v. After the collision, I basically have one object here. The question said the bullet becomes embedded in the block, so the two stick together. So I can kind of, at this point, if I want to, treat them as if they're one object, kind of glued together. So instead of having one object with mass 35 grams and one object with mass 5 kilograms, I now have one new object with mass 5.035 kilograms. And it has a velocity of positive 8.6. Here I've just chosen positive to be the direction the bullet was, or the bullet and block are traveling in. Now I can go through this, multiply these two numbers, divide by 0.035, and I should find my answer is positive 1,237, or 1,237 meters per second in the direction that that everything is moving, which we've drawn as being to the right. So that is how fast the bullet would need to be going at the beginning in order to push the block and itself off with this speed at the end, after the collision. Now, we've been using conservation of momentum to solve two examples where we have collisions. It's also useful in cases where we have explosions, which is sort of the opposite of a collision. In a collision, you have two objects coming together. In an explosion, you have one object splitting apart into many pieces. So let's look at an example of an explosion right now. Example 3. A firecracker sits in a 7 kilogram pumpkin. After it explodes, the pumpkin splits in 2 chunks. A 5 kilogram piece travels west at 10 meters per second. What is the mass and velocity of the other piece? Let's start, as always, with our initial and final T-chart. And a quick diagram. So here I've drawn everything we know about the problem. The pumpkin, stationary at beginning, is 7 kilograms. Firecracker inside it goes off, and this chunk is flying west at 10 meters per second. It's a 5 kilogram chunk. We want to know what the other chunk is doing. What's its mass? What's its velocity? Well, the mass is fairly straightforward to figure out. If the whole pumpkin's 7 and this chunk is 5, then the remaining chunk has to be 2. And the velocity we'll have to figure out using conservation of momentum. So let's go to that formula. Initially, there's no momentum here. Just one pumpkin sitting, not moving. No velocity, so no momentum. In the end, I've got this mass times this velocity to give me a momentum, and this mass times this velocity to give me another momentum, and I'm going to add those together to sum them. Now it's just a matter of doing some math. So we see that the velocity of the small chunk of the pumpkin is going to be 25 meters per second. I get a positive number here, so that means it's going to be going to the east. Okay, now there's one last thing I would like to talk about, and that is sort of types of collisions. The 2 collisions we looked at before, we said had 2 different types. Here was a collision where the objects kind of separated and went different directions after they collided, and here was a collision where they stuck together. There's some reasons for this, and some names for these types of collisions. So we're going to talk about what are called elastic and inelastic collisions. When I think of the word elastic, I think of like an elastic band. I think something that's really springy, really bouncy, like maybe a bouncy ball. And an elastic collision is what you would maybe expect to happen if 2 bouncy balls collided. They would bounce off of each other, and they would come flying off in opposite directions with pretty similar to speed to what they hit each other with. In other words, the kinetic energy would be conserved. They're coming in with a lot of speed, but because they bounce so well, they're going to be heading out with a lot of speed too. So the objects will separate and the kinetic energy is conserved. Lots of kinetic energy at the beginning, lots of kinetic energy at the end. Now, it's tough to make a ball that's perfectly bouncy. And there's lots of things we make that are designed not to bounce. Think maybe, like a tennis ball or something like that. Yes, it bounces, but every time it bounces, it doesn't go quite as high as the last time. It'll bounce off something and head off the other direction, but not quite as fast as it came in, not with quite as much kinetic energy as it came in. So this is what's called an inelastic collision. It might bounce a little bit, but kinetic energy is not conserved. It's lost. And then what we have is a perfectly inelastic collision. This is where not only did we lose kinetic energy, we lost as much kinetic energy as possible. And the objects are moving as little as they possibly can after the collision, meaning they have stuck together. Here's where you can think of maybe a collision between two beanbags. They're not going to bounce off each other. They're just going to deform and kind of stick together in one lump. So let's look again at example 1 and think about whether it's elastic, inelastic, or perfectly inelastic. We already know in example 1 that the pool balls bounced off each other. They didn't stick together. One was going west and one was going east. So we can probably say this was not perfectly inelastic. We can probably cancel that one out because it requires them to stick together. But the problem could be elastic, meaning kinetic energy is conserved, or it could be just a little bit inelastic, meaning kinetic energy is not totally conserved. Now I'm looking at this problem, I'm thinking they came in pretty hot, 4.5 meters per second and 5 meters per second, and they came out going significantly slower, 2 meters per second and 1.5 meters per second. So my hunch is that there's a little less kinetic energy at the end, so kinetic energy is not conserved, so I think this is going to be an inelastic collision. But we should double check that. So let's find the total kinetic energy initial. Kinetic energy, I'll remind you the formula for that is 1/2 times m times v squared. So I have 1/2 times the mass of the cue ball times its speed, 4.5 squared. And then I've got the 8 ball as well. Its kinetic energy is going to be 1/2 times its mass times its speed squared. Again, in this formula, this v is speed, not velocity. So it's a scalar, not a vector. Direction does not matter for kinetic energy like it does for momentum. We can also find the total kinetic energy final. So for the cue ball, 1/2 m v final squared. And for the 8 ball, so let's go through and calculate these two numbers, see what we get. Okay, so we see that the total kinetic energy initial for both balls was 5.66 joules, and the total kinetic energy final was 0.781 joules. So as we suspected, a lot less kinetic energy coming out than going in. So kinetic energy was not conserved, so this is an inelastic collision. It's not perfectly inelastic, because they didn't stick together, but it is inelastic. Okay, and that sums up our lesson on the law of conservation of momentum.